So yeah, I'm Georgios, I'm from NIL Foundation, and I'm going to talk about vectorization with AVX-512 for speeding up crypto operations in zkEVMs. So what is AVX-512? So it's a family of vector extensions, usually used to parallelize certain operations. And there are different vector extensions supported by AVX-512. The first one is AVX-F, which uses a 32-bit multiplier. And the second one is the newest set of extensions, IFMA, which supports 52-bit multiplier. So what happens is AVX-512 by default uses the 512F vector extensions. If a CPU supports AVX-512, then it uses this set of extensions. Otherwise, the IFMA are optional. It means that currently they are not supported by all processors. The processors that support IFMA instructions are Cannon Lake, Ice Lake, Tiger Lake, and Rocket Lake. However, in the future, Intel plans to integrate IFMA instructions to all processors. So initially, vectorization and vectorized implementations were used for accelerating image processing and video processing. However, it became evident that they can be also used to accelerate cryptographic operations, especially in cases where you're working over large fields, like the case of elliptic curves. When it comes to crypto implementations, I think we were the first to use IFMA instructions. And basically what we did is we implemented isogeny-based protocols. And a couple of years ago, we have seen some IFMA implementations of lattice-based schemes, especially Kyber and dilithium. So these are both families of algorithms in post-quantum cryptography. But when it comes to classical cryptography, we have seen some libraries for elliptic curve crypto systems. What we would like to do is to see whether these IFMA instructions can help us improve the performance of protocols that are used in zkEVM. For example, we have BLS signatures that we would like to investigate and the aggregation functionality. And we also have polynomial commitment schemes like KZG, which uses elliptic curves, and Fry polynomial commitment scheme. We started with the first use case, the BLS signatures, and we have a software which we call AVX-BLS. And well, the target is to vectorize the whole BLS signature scheme, but we started with the first step, which is the implementation of the optimal 8 pairing on BLS 12381 curve. So this was the first step that we vectorized, and in the future we plan to vectorize the whole signature scheme. This is a joint work with Hao Chen, Johan Grossedel, and Dan Page. And we have a paper which is currently under review, and we expect to have some results next month. Okay, so just a recap on how the optimal 8 pairing works and BLS 12381 curve. BLS 12381 is a pairing-friendly elliptic curve with a bending degree 12. It has an equation of the form y squared equals x cubed plus 4, and it is defined over a base field of size 381 bits. It has a composite order, and in particular, it has a prime factor of size 255 bits. And one important property is that it admits degree 6 twists. And this is an important property because this is what can help us improve the performance of the optimal 8 pairing. When it comes to the optimal 8 pairing, how does it work? So basically, the optimal 8 pairing takes as input 2 points, Q and P. The first point, Q, is defined over FP squared, while the second point, P, is defined over FP, over the base field. And the optimal 8 pairing is executed in 2 steps. The first step is the Miller loop, which computes this Miller function F. And then the second step is to raise this Miller function to the exponent p to the 12 minus 1 over r. This is called the final exponentiation. So I'm not going to describe how the optimal 8 pairing actually works, but what is important is to understand what kind of operations we're using in this optimal 8 pairing. And basically what we're using is arithmetic over a big field, fp to the power of 12. And what we want to implement is multiplication, squaring, cyclotomic squaring, sparse multiplication. These are all expensive operations because they're executed over a big field. We also have arithmetic in subfields of fp12. We have arithmetic in fp, fp square, fp4, and fp6. And of course, we have arithmetic over elliptic curves. We have point doubling, point addition, and we need to do some line computation and line evaluation. Now, before starting our vectorization, we wanted to identify which are currently the libraries that have the most efficient implementation of the optimal 8 pairing. And there are actually two choices. The first one is the BLAST library. This is implemented by ZKs. And in fact, this library is an implementation of the whole BLS signature scheme. And it's currently integrated and used in Ethereum. So this is the reason why we use the BLAST library as a reference for our comparison, but also our whole implementation is basically a vectorized version of the BLAST library. Now, the second option is an implementation by Patrick Longa. This is based on the Relic library. Relic is a very well-known library that implements a variety of pairings. And Patrick's implementation is slightly faster than BLAST. It is faster by a factor of 1.07. And the reason is that Patrick is using a different implementation of the cyclotomic squaring. Their method is called compressed cyclotomic squaring. When it comes to the BLAST library, what we wanted to do is to identify which are the most expensive operations executed in the Miller loop and the final exponentiation. For the Miller loop, the most expensive operations are squaring over the big field over fp12, sparse multiplication again over fp12 with 32%, and point doubling and computing the double line. So these three are the most important operations and the most expensive operations in the Miller loop. While in the final exponentiation, around 74% of the total computation is spent on cyclotomic squarings, and around 18% on multiplications over fp12. So if we want to optimize the optimal 8 pairing, these are the core operations that we need to target and we need to optimize. So how does our vectorization work? In the beginning, I should say that if we want to represent an integer a over fp, what we do is we split it in limbs. So basically, an integer over fp, where in our case p is 381 bits, is split to 8 limbs. Each limb has size 48 bits. And in the case of vectorization, we're working with what we call limb vector sets instead of integers. So we can represent 8 integers over fp using an array representation. What it means is we can construct an array where each column of the array contains all limbs corresponding to an integer. For example, we can say here that the first column has all the limbs corresponding to integer a, second column has all the limbs corresponding to integer b, and so on. So this is an 8 times 1 limb vector set because it uses 8 lanes, 8 columns to represent the limbs of every integer. But you can also do a 4 times 2 way limb vector set, which means that you can use 2 columns to store all the limbs of one integer. For example, in this case, you have column 1 and 2 containing all the limbs that correspond to integer a. And in order to do a vectorized multiplication over fp, what we did basically is we vectorized Karatsuba multiplication with Montgomery reduction. And what we did is we replaced the single instructions with vector instructions. And we ended up with an algorithm that performs 8 multiplications over fp in parallel. Now, moving one layer up, we have arithmetic over fp square over an extension field of degree 2. And if we want to do multiplication over fp squared, there are two formulas that are usually used. The first one is Karatsuba, and the other one is schoolbook. Normally, if we consider sequential implementation, Karatsuba is the fastest option, especially over large fields. But when it comes to vectorization, this is not always the case. What we did is we implemented the schoolbook method, and in particular in four-way parallelization. It means that we're executing 4 multiplications over fp squared in parallel. And for that, we need 2 8 times 1 limp vector sets, where each limp vector set contains 4 fp squared elements, and each element in fp squared has 2 fp components. So basically, each limp vector set represents 8 integers in fp. And these are the speedups that we got. This is in green here. We can see that our vectorized multiplication over fp squared gives us a speed up of 3 times compared to the BLAST library. While in the case of fp squared squaring, we get a speed up of 2.54. Now again, moving one layer up, we have elliptic curve operations. And here I will describe point doubling and computing the line in the doubling step. So in BLAST, points on the curve are representing projective coordinates, and in this case, we have a point T with 3 coordinates, and all coordinates are defined over fp squared. If we want to compute the double of the point T, we need to implement this formula here. We need to do a bunch of squarings and multiplications over fp squared, using the coordinates of the point T. And if we want to compute the line, the tangent line that passes through T, then this will have 3 coefficients, L0, L1, and L2. And again, in order to compute these coefficients, we need to do a bunch of squarings and multiplications over fp squared using the coordinates of the point T. So what we did is we vectorized this the algorithm that was already implemented in BLAST, we vectorized it in 4-way. It means that we're executing 4 fp squared operations in parallel. For example, in step 2, you can see that we're executing 4 squarings in fp squared in parallel. If you consider the original BLAST implementation, all these instructions are executed sequentially. And the speedups that we got for the doubling process, we got a speedup of 1.93 compared to BLAST, while in the case of addition, point addition and addition line, we got a speedup of 1.69. The difference is that in the case of addition, we were only able to do a 2-way parallelization, not 4-way. And here are some results regarding the fp12 operations. Here I consider the fp12 cyclotomic squaring, the fp12 multiplication, fp12 sparse multiplication, and fp12 squaring. With blue, corresponds to the BLAST library, red corresponds to Patrick Longa's implementation, and green corresponds to our AVX BLS software. And in all cases, we got a speed up between 1.88 to 2.26. We also did some additional vectorization of operations in FP4 and FP6. These operations are required mainly in the final exponentiation. Now, what about the performance of the pairing? Here we can see that we managed to reduce the execution time of the Miller loop to half. So we only need 500,000 cycles for the Miller loop. This gives us a speed up of 2.01. For the final exponentiation, we got a similar speed up by a factor of 1.94. And for the total pairing computation, we got speed up of 1.97. So now we have our pairing is executed, one pairing computation is executed in 1.2 million cycles. There are some additional tricks and modifications that we need to do to our code, and maybe we will be able to reach a speed up factor 2, maybe a bit more, but this will be done near future. As well, our paper source code will be available probably late June. Now, as I said in the beginning, our goal is to vectorize the whole BLS signature scheme. And in order to do this, we are missing some operations. And here you can see the different layers where we applied our vectorization. We started with arithmetic over FP, we moved to arithmetic over extension fields, then elliptic curve arithmetic, and everything that is in red, we still need to vectorize in order to have a vectorized implementation of the BLS signature scheme. And two operations that are important to be vectorized are the process of hashing to curve. This is starting from a random bit string and mapping it to a point on the curve. And scalar multiplication. We also need to vectorize scalar multiplication. And also, we are interested in looking at ways to use our vectorization strategies to accelerate the signature aggregation process. So these are things that we'll be investigated in the near future. One other use case that we would like to have a look at is the implementation of the KZG polynomial commitment scheme. So KZG also uses pairings. It uses pairings on a different, it uses the optimal pairing on a different curve, the BN254 curve. But there are many similarities, and we can reuse our code for this pairing as well, because the extension fields that are used are the same, and other functions can be easily adopted in the case of BN254 curves. Another use case that we would like to have a look at is the Frye polynomial commitment scheme, and how we can use our vectorization to improve the performance of Frye. So the trend, in terms of Frye, the trend now is to use small fields, like either 64 bits or 31 bits, both in Frye and circle Frye. But you still need to do operations in extension fields. And you also need to do polynomial arithmetic, scalar multiplications. So these are all things that we are planning to investigate, how we can use our vectorization to improve the performance of Frye. And yeah, that would be all.
Just for the AVX-512, you mentioned when you're looking at the actual ability to put this on hardware, it was predominantly on Intel. Is there, so that you're not so reliant on Intel for the actual hardware, is there independent like ASIC or other ability to run this accelerated compute on separate hardware, so you're not reliant on Intel chips?
Sorry, could you repeat?
Is there other hardware? So like you mentioned to be able to
be able to run our vectorization, let's say, in other types of hardware?
Yes, you're using the AVX-512 library, but
yes.
It seems like a lot of it is predominantly on Intel silicon. So
yes.
So it's great work that you're doing using this library, but is it possible to use this on other hardware, either dedicated independent chips?
Other hardware that supports vectorized instructions, yes, because our vectorization is generic, so you can easily adapt it to other things, like GPUs, for example. You can still use vectorization, and in particular, our strategies for extension fields and stuff, you can use it, yes.
So you said that Relic implementation by Longa is faster than BLAST because of compressed cyclo. So is it like Carabina algorithm? So which compressed algorithm? So, and the second question is, so are you using this compressed algorithm in your AVX implementation, or are you using the BLAST one?
Sorry, can you repeat? I'm not hearing very well.
So at some slide you said that Relic implementation by Patrick Longa is faster than BLAST because of the use of compressed, so I assume it is Carabina algorithm for the compressed cyclotomic square. So the question is, in your implementation with AVX, are you using the same algorithm as Relic or BLAST?
Blast.
Okay, so
we use the cyclotomic squaring.
So it's faster even if you're using the old version. Okay.
Yeah. Yes. But we also try. So what happens is, if you replace the cyclotomic squaring implementation in Blast with the compressed cyclotomic squaring, Blast becomes faster than Patrick's implementation.
Okay.
Slightly faster, but still faster. So we also did that.
Okay.
Thank you.